Logarithm, introduced by John Napier in 1614 for the purpose of simplifying calculations. It plays very important role in the mathematics, but today this is not limited in mathematics, but it is being used in every branch of science and engineering. In this slide, a brief explanation of logarithm, its graphical representation, and some example operations will be discussed. Before I talk about logarithm, I want to talk a bit about the exponential function, and this will help us for better understanding of the logarithm. The exponential function is like this. In this equation, b is the base, x and y are variables, and the condition of the equation is b must be greater than 0 and b must not be equal to 0. In these conditions, the equation is called an exponential equation, and we can say that y is the exponent of base b. Let me put some values in the equation 1. The equation 1 is b to the power y equal to x. I have chosen the value for base b equal to 10. Here is the example values of y from 0 to 5. It produces the value for x on the right hand side from 1 to 100,000. If you have a closer look, you can observe the changes for b to the power y equal to x. The graphical representation of equation 1 for the base b equal to 10, it's like this. The equation is b to the power y equal to x. The green line shows the behavior of the equation 1. In the x-axis, the values of x are being coordinated, and in the y-axis the values of y are being coordinated. And you can observe that when y equal to 0 and the value of x equal to 1, and when the value of y equal to 1, the value for x equal to 10. So now we are turning to the actual discussion point of this slide. What is logarithm? A logarithm function is the inverse function of an exponential function, which is defined as log base b of x equal to y, as I denoted this equation as equation 2. Here b is the base, x and y are variables, and the condition of the equation is b greater than 0 and b not equal to 0. Let me put some values in the equation 2. Equation 2 is like this, and I have chosen the values for x from 1 to 100,000, for example, and these numbers based b equal to 10. And you can observe the changes on the right hand side. I'm changing the numbers format. We can write the numbers in this power form. So you can observe that for the value of x equal to 1 to 10 to the power 5, it produces the value of y from 0 to 5. And this is the graphical representation of equation 2. And the green line indicates the behavior of the equation 2. In the x-axis, all the values for x are coordinated. In the y-axis, all the values of y are being coordinated. And you can observe when x equal to 1, y produces the value is 0, and when x equal to 10, it produces for the value of y equal to 1. Let's see the difference between equation 1 and equation 2 in a closer look. In the left hand side, I have put the equation 1 and its example values, and on the right hand side, I have put the equation 2 and its example values. You can see the changes, the values of equation 1 and equation 2. It's surprising but true. The graphical representation of equation 1 and equation 2, it shows the same graph for both equations. Where for the value of y equal to 0, it produces the value of x equal to 1, and for the value of y equal to 1, it produces the value of x equal to 10 for both equations, and those both equations are based b equal to 10. For product, quotient, power and root of numbers, logarithm has some formulas. Number 1, if x equal to b in the equation 2, then log base b of b equal to 1. For example, log base 2 of 2 equal to 1. Number 2, for product, this is the formula of product. This formula allows us to split the product from of this x and y to its addition form, like this shown in the screen. For example, log base 2 of 32 equal to log base 2 of 4.8. According to the formula, finally we got the values of log base 2 of 32 equal to 5. Number 3, for quotient. This is the formula for quotient. For example, number 4, for power. For example, number 5, for root. That's the formula for root. For example, the base b equal to 10 is used for the common logarithm. It is mostly used in science and engineering. For example, for base b equal to 10, so we can say that for base 10, the logarithm of 1000 is 3. The base b equal to 2 is used the binary numbering system, which is mostly used in computer science and engineering. For example, for base b equal to 2, we can split 128 like this. As 2 to the power 1 equal to 2, by default every number has the power of 1. So we can say that for base 2, the logarithm of 128 is 7. The base b equal to 8 is used for the octal numbering system, which is used in some field of engineering. For example, base b equal to 8, log base 8 of 512 equal to what? We can split 512 8 times 8 times 8. So we can say that for the base 8, the logarithm of 512 is 3. For natural logarithm, the base b equal to e, Euler Constant, is used because of its easiness of finding the derivatives and integral in calculus, which is mostly used in mathematics, physics, chemistry, statistics, economics, information theory, and engineering. When the base b equal to e is used, the logarithm is written as log base e of x equal to ln x. That means we can pronounce this ln x. And the value of Euler number e is 2.71828. For example, the base b equal to e, log base e of e equal to 1, and log base e of 512 or ln 512 equal to 6.238324 using the calculator. So we can say that for base e, the logarithm of 512 is 6.238324. Logarithms can also be negative. For example, so we can say that for base 10, the logarithm of 0.1 is -1. Example 2. So we can say that for base 10, the logarithm of 0.01 is -2. Example 3. So we can say that for base 2, the logarithm of 1/16 or 0.0625 is -4. If you like this video, please support us. Thanks for watching.